Hi folks, my name is Emily Weber. I'm a machine learning specialist solutions architect at Amazon Web Services. I'm joined here today by Yu Guo. Yu is a senior manager of perception at Aurora, and today we are here to learn about large-scale ML models and training these on Amazon SageMaker and on AWS. So let's get started. And as a quick reminder, this is, in fact, a 400 level session. So what that means is we're going to be diving into the code, we're going to be diving into the complex topics. We're assuming some base level of understanding of machine learning. We're assuming that you're happy actually talking about advanced technical topics. So that's what this is really about. So we're going to cover three components today. First, we're going to learn about very large-scale training on SageMaker. So remember, SageMaker is a fully managed service within the AWS portfolio. And so we're going to understand how we can use SageMaker for training extremely large deep learning models, be those natural language processing, computer vision, XGBoost, you name it. If you can write it in open source software, you can in fact run it on SageMaker. So we'll take a look at that. After that, Yu is going to walk us through perception at Aurora. Aurora has some really interesting stories that they'd like to share with you around how they're using computer vision and deep learning in particular to drive. So you'll learn all about their self-driving technology. Both of those sections are going to include a quick demo, and then we'll cover some resources at the end of it. So sit back, relax, and enjoy the ride. All right, so deep learning on SageMaker. So we're aware that big machine learning models are popular these days, right? Everyone's heard about GPT-3, everyone's heard about BERT, but are they really worth it, right? What's really interesting, what's exciting about these large-scale models? And so the screenshot you see here, the image is from a paper that most of you probably know, and that paper focuses on a model that's called GPT-3. Now, there are three different experiments that you're seeing in this paper here, in this diagram. So this green line down here at the bottom is a model with, say it with me, 1.3 billion parameters. So still a lot, definitely more than, say, a billion parameters. Remember, the parameters are the weights and the biases that are actually composed within the model itself, and they help it learn. And so that's a model with 1.3 billion parameters. And now if you look over here on the y-axis, you'll see that 1.3 billion parameter model clocked in at about 5% accuracy. So not much to write home about. When you increase that model by 10, so 10x increase, drop that up to 13 billion parameters, the accuracy also goes up, right? So we went from 5% to right around 25%. So definitely exciting, definitely better. Not quite enough to make an investment, but still worthy of note. But then it's the next jump up here that everyone is talking about these days. And so that is this large model, 175 billion parameters, which hit a 65% accuracy level in this specific data set. Using pretty much the same model diagram, right? The architecture of the model, the layout of that graph was nearly identical to its predecessor GPT-2. Included a few efficiency gains, but generally speaking, it's the same model. It's just a lot larger, and that's why they call it GPT-3. And so GPT-3 and similar, deep learning models are beginning to approximate human performance, right? In some cases, actually going beyond human level performance. Now, remember, these are all very, very scoped. So on very specific data sets, on very specific subsets of problems. But when used in the context of a larger system, for example, at Aurora, they can do some pretty impressive things. And now in computer vision, we definitely see some large models. I haven't quite seen, CV models that are at the full scale as what NLP is crunching out these days. But it's also helpful to note that there are many open issues, right? There are open issues with large language models on cost, on environmental concerns. The bias in these models is real and is something to consider. So generally speaking, use with caution, but proceed, because there's fun stuff to look at. And so remember, we're here to talk about large-scale distributed training. So first, let's understand why this is challenging, right? Why isn't everyone doing this? So the science of it, the pure, concepts, the pure methods around defining the model, solving the business problem well, ensuring that the model is performing, that kind of pure ML science, applied in research science, that data science aspect. Obviously, that's challenging, right? We're all familiar that is time consuming. The system design of it is also complex. If you're looking at how to store your vectors, how to optimize for your caching, how to ensure that your overall system architecture is performant, is low cost, is as fast as you need it to be, is secure. Generally, that sort of system level analysis is challenging. We see a lot of issues with compute utilization, where GPU utilization can spike and then drop, flatline. It can stay low. It's actually pretty rare to have GPU utilization be stable. And the reason we care about stable GPU utilization is because that means your job can scale more effectively. So if your GPU utilization is nice and happy at this like steady state medium, that means A, you pick the right EC2 instance, but B, it's scaling effectively, right? You're able to grow and add more instances to that cluster because of that stable GPU utilization. If it's really, really spiky, then you can throw more compute at the problem and it's going to make things worse, actually. It may not make things better because you're not getting that clean scaling efficiency. And then the last reason why large-scale distributed training is challenging is just the pure platform management of it. Just turning on those instances, turning them off, making sure they have the right packages installed, making sure they have the right, images and software that you need, troubleshooting these, debugging them, health checking the instances, doing metadata management. All sorts of these are challenging aspects. And so on Amazon SageMaker, we take care of this for you. SageMaker is a fully managed machine learning service. Here at re:Invent, you can learn about using SageMaker Studio. You can learn about SageMaker endpoints. Today, we're going to focus on training. And so the heart of SageMaker training are these ephemeral instances, right? These ephemeral EC2 instances that are, again, fully managed by SageMaker, so they're not going to show up under EC2, they'll show up under SageMaker. And you define the cluster config. You can define how many instances you need, what type of instance you need, what size you need, whether you want to run these, in your VPC or in the service VPC. You get to define these, bring all of your packages, all of your requirements. We're going to turn on your instances for you. We'll copy in your data from S3. We will copy in that image from ECR, and we're going to run this, right? That cluster is fully managed. You can view all the metadata from this. You can search all the logs from these. You can view them in CloudWatch. You can, consolidate the views in SageMaker Studio. You can deploy them to endpoints. You can orchestrate them in pipelines using Kubeflow components for SageMaker, all sorts of things. You can also bring your own deep learning models. So in this view, we're looking at what's called script mode in SageMaker. And script mode in SageMaker boils down to this. You're importing an object that is a pre-built container. So it's a pre-built container that is defined for the version of deep learning that you'd like to use. So if you're building a PyTorch model, MXNet, Chainer, scikit-learn, XGBoost, any number of these frameworks, you can bring your own deep learning model in the form of a script, right? So you can just bring this basic script, bring your framework version, define your instance configuration, add your hyperparameters, point to your dataset, S3, call model.fit, and then whether you're calling that model.fit, whether you're literally executing that from a Lambda function or from your laptop or from a server or from, I don't know, maybe a Snowball Edge, some like disconnected device, wherever you execute that, it's going to point to the AWS cloud and then actually run your content there. So we learned that you can bring your own deep learning models and then scale these on SageMaker efficiently. You can also lower the cost of your training using managed spot instances. So spot instances are really popular at AWS. They're a nice way to just take cost out of your equation. And so using spot instances is really easy on SageMaker. You're going to add 3 hyperparameters. You're going to add use spot instances, set that to true. You're going to add a max wait time and a max runtime. And so once you use both of those 3 hyperparameters, we will default to using spot instances. Now, a word of caution, If you're running extremely large scale jobs, we don't necessarily recommend using spot instances because the capacity issues are real, right? We're in this pandemic, everyone is experiencing the chip shortage. And so if you're running large scale jobs, we recommend not using spot instances because you're just more likely to get the capacity that you need. Yeah, and so that's recommended. If you're doing just one or two instances, no problem. Definitely try spot. Um, expect that you may have to wait. If your job is interrupted, so long as you're storing your checkpoints in S3, so actually pointing again to an S3 path with that checkpoint parameter, we will revert your job. So we'll take your job config, we'll turn that onto a new instance. So we'll spin up an on-demand instance, and we'll actually execute your job from the point that it stopped. So we'll restart and continue your job from the last checkpoint. You can use SageMaker Debugger. So debugger is a way to plug into the tensors on your model. So while you are training that deep learning model, you can store the tensors back in S3. You can download those tensors to apply built-in rules to them. You can also apply visualization. So here's a class activation map, which is useful in computer vision and autonomous vehicles when we want to ensure that our model is using the right pixels to perform that classification. You can also train extremely large models. So this is a view of what's called SageMaker Model Parallel. So we launched it 2020 reInvent. And Model Parallel will profile your algorithm. So we will look at your custom graph, your custom deep neural net, and we'll actually figure out the optimal sharding strategy. So we'll take all the different nodes in your graph and we will place them onto your GPU devices. So if you're sitting on one P4D, that's going to have 8 NVIDIA V100s, and we will shard your model for you. So we'll take your MNIST, your BERT, your Masker CNN, and we will shard this across all of the GPUs that are available both in single and multi-node settings. And then we'll actually execute them via what's called pipeline parallelism. So using pipeline parallelism, we'll execute the different nodes within your graph at different points in time in order to maintain stable utilization. So it's really easy to use. You just import it in your script and let it do its job. You can also just speed up your jobs. So SageMaker Model Parallel will improve throughput. SageMaker Data Parallel will do the same. So Data Parallel within SageMaker is a new communication protocol. So it is a drop and replace for NCCL on AWS. It is going to be 20 to 40% faster than NCCL and MPI-based solutions, such as Horovod. So if you've followed parameter servers and distributed, deep learning configurations over the last couple of years, you know about parameter servers, you know about this ring-based topology that's used in Horovod. Herring, or SageMaker Data Parallel, brings the best of both of these together. Please read through the paper if you're curious. It's really interesting. But if you are running large-scale jobs on EC2 or on SageMaker using Horovod or using PyTorch Data Parallel, then definitely take a look at Herring, as it will just make your job 20 to 40% faster by default. You can also tune your own models on SageMaker. So if you're using a NLP model and you want to tune for the right number of epochs or the right batch size, or if you're doing the same for computer vision, you can define your own hyperparameter, define your own objective metric, and you can do warm starting, actually. So we'll use this custom Bayesian optimizer that we have, and you can leverage it to train hundreds of models by default. You can also set up a training job for millions of models on SageMaker. Now, the way this works, generally, if you want to train, say, like one model per person in your data set or one model for maybe vehicle in your fleet, what you might consider doing is developing an orchestrator. And this orchestrator, if I were doing this, I would just develop something locally on Studio and then move that into a Lambda function. But this will enable you to, per training job, and remember, these training jobs are logically and physically separated on the AWS cloud. For each of those, you just point to an object in S3, and you point to a training script, And so, what I recommend customers do if they're training millions of models is to set some number of models that you want to train per instance. So, per instance, say you're looping from like 1 to 100, and then you're doing this on 10 training jobs. So then that's 1,000 models. And if you want to do a million models, you just add zeros to both of those things. And so because SageMaker is so modular, it enables these types of very large scale use cases. And then lastly, I am really passionate about hybrid ML. I love helping customers think about how they're training in the cloud and then deploying their models on premises, orchestrating those with SageMaker components for Kubeflow, or any other orchestration toolkit, enabling monitoring for these. Or if you're training on-prem and then deploying in the cloud, there are actually 8 architectural patterns. I just put together a white paper on this a couple months ago, and so you can check out that bit.ly in order to view it, but it should be fun. And so with that, let's check out a demo.
All right, let's check it out. So remember, in this demo, we're going to take a look at SageMaker training. We're going to use Hugging Face in order to do this, and by default, that implies the SageMaker model parallel. Now, to add in a little bit more fun here, we're also going to compile this model for Inferentia. So we're going to deploy a model onto Inferentia using this Neuron SDK, and as luck would have it, that's a different model. So we're going to deploy a BERT model while we're going to be training Roberta using the IMDb dataset. So you'll see this is SageMaker Studio. So remember, we have multiple tabs available here. And before we dive into the training, let's just recap some of these pieces here. So remember, we'll open up this data widget up the top left and just see where we're sitting. So right now I'm in the SageMaker examples repository, which I had previously cloned onto my local Studio notebook. Now, SageMaker Studio has Git branching capabilities. So directly within inside of the UI here, we can see all of the changes that I've made to this notebook and this repository. So again, current repository, SageMaker examples. It's going to track the branch, so we can actually change to different branches. We can add new branches directly inside of Studio, and we can add our changes. So we can add these and then stage them for commits, writing commit messages, and merging them in directly here. You remember Studio has a lot of compute options that are available. Remember, we have one server that's called the Jupyter server within Studio, and that's the primary UI that we're looking at. But then the big difference is that this single Jupyter server is actually farming us out to multiple instances. So all these instances and kernels that we see are actually different machines. So we have one T3 medium, which has just a couple CPUs there, and then one G4 DN, which has one GPU. And they're called kernel gateway applications, and they're connected to our server, to our Jupyter server. So what that means is inside of my single pane of glass IDE here, I can connect into multiple instances. And so I can actually run different instances for different projects. And then lastly, in Studio, if you cruise down to the bottom here, take a look at this little SageMaker Jumpstart icon. So Jumpstart is another feature in SageMaker that has many different examples and tutorials available. So we can search within here. Let's say we want to search for Hugging Face. And so we'll see many different models that are available. We can pick GPT-2, and then we can just deploy a pre-trained GPT-2 model. We can also fine-tune, apparently not GPT-2, but other models. We can fine-tune them via Jumpstart. And then if we cruise down to this triangle, we'll see, and then click on this dropdown. So remember, we have SageMaker pipelines, we have endpoints, experiments, the model registry, feature store, data wrangler, MLOps with pipelines, all sorts of goodness. But today we're going to focus on training. So the notebook that I have in store for you is going to focus on a simple technique. And now this technique is really powerful. And if you are already familiar with AWS, already familiar with things like picking the right EC2 instance, this is going to be pretty basic to you. But if you're new to picking an EC2 instance, then you might find this pretty surprising. What we're going to do is we're going to upgrade our training instance. So we're going to run 2 jobs in this demo. And the first job is on an instance that's called a P3.2XL. So P3.2XL. And I'm just going to zoom ahead here so we can just get to the punchline. So the P3.2XL has 1 NVIDIA A100. So that's 1 GPU. We're going to run the same job on a larger machine. We're going to run exactly the same config, the same scripts, the same hyperparameters on a larger machine. That larger machine is a P3DN24XL, which has 8 NVIDIA A100s. And the good news is that that means our job is going to go faster. So we're going from 1 GPU to 8 GPUs, and so that's why we call that horizontal scaling, actually, because we're sort of adding, more cores here. So 1 GPU, 1 to 8 GPUs, and now the impact of this is that our job will go faster. The reason it's going to go faster is because, again, Hugging Face, the SDK, uses SageMaker Model Parallel by default. So that base trainer API is integrated with SageMaker Model Parallel, which means we're going to take advantage of all 8 of those GPUs instead of just the 1. Let's take it from the top. So the first thing we're going to do is, and this is no surprise, we're going to install a whole bunch of packages. So we're going to update the SageMaker Python SDK. We're going to pip install the Transformers SDK and then that Datasets SDK for Hugging Face. So we'll do that right here. We're also going to update PyTorch. So we've got PyTorch updated here, and then the Neuron SDK. Now, the Neuron SDK is not easy to install. It's quite a few arguments here in this pip install. So just make sure you really get this directly from an example notebook. This line will work, but if you make changes to it or remove some of the content, it may not work. And then after that, same flow as normally, we need to restart this kernel. So we actually need to turn this kernel off and then turn it back on in order for the libraries to become available. And so we'll do that here, and then we'll say import Hugging Face. So then after that, we're going to do the typical steps, right? We're going to point to our bucket. We'll set up our SageMaker session. All these we can change, but this is just the default here. And then I'm going to point to a tokenizer for Roberta. And remember, Hugging Face is great because they make it so easy. We're just going to type in the name of our tokenizer and the name of our model, and it's going to generate all the stuff for us, right? It generates all the code, which is great. And so here, I'm loading an IMDb dataset. So I'm just loading that also through the Hugging Face SDK, and I'm downloading this tokenizer. And then I'm applying the tokenizer in the form of loading the dataset here, right? So we're loading this dataset, we're splitting it into our train and test set, and then making sure those are downloaded, right? So you see the download came through, which is great. The next thing we're going to do is save that out to S3. So remember, SageMaker likes it when our data set is sitting in S3 or in the cloud. Remember a couple other options there, but typically you'll start with your S3 bucket. And then this datasets SDK is going to let us save directly to S3 instead of like literally to disk locally, which is kind of nice. So we're saving to S3. And then the next thing we're going to do is set up our estimator. So remember, we learned about this concept called script mode, where script mode is pointing to a pre-built container. This is a pre-built Hugging Face container, which will take our entry points. So this is a local script, local, content that's defined here. You can also point to the examples on GitHub, actually. So the SageMaker estimators take a Git config where you can point to basically branches and then directories inside of Git repositories just on GitHub or other Git solutions. And then you don't even need the example script. You can just train directly from GitHub. But in any case, we're going to define our hyperparameters here. So I've got those defined, and then my version of Python, my version of the SDK, PyTorch, all sorts of goodness, debug hook config just for fun, and then remember that's the P32XL. So we got the P32XL here. Now I'm going to train exactly one thing. Change exactly one thing. I'm changing my instance type. So now I'm going to point to a P3DN24XL. So that's here. So we've got this new instance type that I'm pointing to. Still just one instance. Everything else is the same. We're going to call model.fit. And so you can also visualize your models using Debugger, Debugger within SageMaker, actually. So essentially, Debugger will collect your tensors, and then from your tensors, you can visualize them and apply some built-in rules. We're going to continue on here. That's a different model, but still fun to see, but a different model. And so we're going to compile this pre-trained RoBERTa model using the Neuron SDK so that we can deploy it onto Inferentia. So in order to do that, we take a pre-trained model, and actually this is the BERT model that we're compiling. So we'll take the BERT model. This is a pre-trained BERT model, and we're going to load this into the model step. So get it to a point where we can call model eval. So we'll call model eval right down here and ensure that we can see all of the different layers and make sure that that's valid. And then once we have that, we're going to load it into torch.neuron.trace. So again, this is using that Neuron SDK here. And so we're passing in the model, a couple example inputs, and then this really helpful parameter that's called strict equals false. So this is great. Basically, when you set strict to false, that means you don't have to compile literally every single operation. You can compile some of them, and then the ones that weren't supported at that point in time they'll just stay the same. But the other ones will actually get compiled for your target hardware, which is great. So we've got this graph that we compiled with the Neuron SDK, and then we're going to save that to disk. So now that it's saved to disk, we're going to compile this, or rather wrap it in a tarball, which we all know SageMaker loves. So we'll wrap that into that tar.gz format, and we're going to drop that into S3. So we uploaded that to this new S3 path. That's right over here. Now we're going to deploy that onto Inferentia. So first off, you need a base image that has the Neuron SDK and that works with SageMaker. This one is actually a public image. If you look in the Neuron SDK examples, you'll find this base image referenced. And this we're going to point to this as a base in order to deploy our model. And so again, using this Hugging Face kind of config here, so we're pointing to the model, right? So we've got that hub set up. So we've got the environment for the model defined, and then same flow. I have my transformers version set up here, PyTorch and Python, execution role, the model path, which is actually in S3. Remember, so that's the model data sitting in S3, that base image, and then this inference.py script. And so I went over that pretty quickly, but so we have an inference.py script, which has these 4 functions we need. We've got the model function, input function, predict, and then output. And then we also have our training script. Remember, so when we trained those RoBERTa models, we essentially are using this if name equals main construct. And then from that, we're defining our arguments. So heavily using argparse, which you'll see in all SageMaker examples. So really using this argparser here, pointing to those environment variables. Remember, SageMaker is actually passing into your container different environment variables that point to things like where your data is, where your different channels are, the number of GPUs, so on and so forth. And then we're going to load in our data sets, just loading those in from disk. Again, this is happening in the training container itself. And then this training argument is coming from Hugging Face. So we're setting up this trainer, these arguments here, and then the trainer instance itself that's taking these pieces here. We're going to call it train. We're going to evaluate. And then once that's finished, write that out to disk and save the model. And so that is what we did when we trained both of those Roberta models. Now we're going to take a BERT model and deploy that onto Inferentia. And so once we have that model compiled, we're going to do this nice step called .isCompiledModel. We're going to set that to true, and then we'll deploy this out. And so now let's hit something against it. So we're going to take the endpoint. So that is the endpoint that I created, wrap this into a predictor. And then we're going to call model the predictor.predict. So just get some quick results here again on this BERT model. So we'll do that twice. And then we'll do some benchmark testing. So this is a set of functions here that just gives you random text, actually, for the purposes of benchmarking. And then we'll look at this at our quantile. So at the 50th percentile, clocking in at 18 milliseconds, 90th at 19 milliseconds, and then 95 at 20 milliseconds for a BERT-based model. And then we'll do some quick analysis. So really quickly here, just moving on, we're going to look at the throughput on those two instances. Remember, we ran a baseline job on that 2XL, and then we ran an upgraded job on the 24 DN. And so obviously the upgraded one has higher throughput. So it's actually more samples per second because the amount of model that's sitting in each accelerator is smaller because it's sharded. And then just a couple quick evaluation stats. We can see that the upgraded instances are about 30% faster in terms of total training time. And then if you're curious, we can cruise out to the SageMaker console. So remember, you can always see your SageMaker content both in Studio and in the console itself. And so we have these two jobs, right? We have the that smaller model, and then this much larger one on the P3DN. And so remember, all of your metadata when you train in SageMaker is stored. All of the arguments, the hyperparameters, the data locations, the results, all of it, the logs, your utilization metrics, and then your S3 model data sitting in S3 is all stored. And so with that, that's the end of this demo.
All right, I hope you enjoyed checking out Hugging Face on SageMaker, upgrading your training instances, and then deploying onto Inferentia. And so with that, I'm going to hand it over to Yu Guo so we can learn all about perception ML models at Aurora. Yu, it's all yours.
Thanks, Emily. Hi, everyone. My name is Yu Guo. I'm a senior engineering manager working on the perception team here at Aurora. Aurora's mission is to deliver the benefits of self-driving safely, quickly, and broadly. And to do that, we built the Aurora Driver. The Aurora Driver is a self-driving system designed to operate everything from people-moving sedans to goods-moving trucks. Aurora develops partnerships with transportation networks, vehicle manufacturer, and the Aurora Driver delivers the benefits of self-driving to the world through these partnerships. Teams at Aurora have been investing in fundamental technologies such as LiDAR that allows us to see several hundred meters down the road, offline simulation capabilities that allows us to develop dramatically more safely and efficiently, and importantly, it gives us enough data to ultimately validate the system and have confidence that it's safe to put on the road. And with that, let's dive in. The Aurora Driver must understand the environment around it, reason about other actors in it, determine the appropriate course of action, and execute that action in a safe way. Our perception system, powered by deep learning, provides an unparalleled understanding of the surrounding environment, allowing for precise decision-making in real-world scenarios. And after refining our self-driving technology on the freight corridor between Dallas and Houston, we've begun pulling commercial loads for FedEx with our new Aurora Driver beta release. Aurora Driver beta brings our upgraded hardware and autonomy system together with key capabilities that enable our trucks to safely navigate both highways and surface streets. Let's explore how Aurora's perception system leverages the complementary capabilities of multiple sensors and combines it with deep learning to produce a rich understanding of the world around the Aurora Driver. Aurora's perception stack is powered by 3 task-specific deep learning modules: Sensor to Tensor, which is our detection engine; Sensor to Adjustment, which is a recurrent tracker; and Remainder Explainer, which helps explain everything else in the environment that the driver needs to care about. These are combined in an object persistence engine to provide seamless scene understanding to the driver. For example, in the one part of our perception system, Sensor to Tensor, our deep learning detection module that uses sensor fusion to learn and infer from multiple sensor modalities, creating a deep understanding of the world around the Aurora Driver. Our state-of-the-art early sensor fusion approach preserves the complementary strengths of the different sensor modalities and progressively fuses them along with map information into a common view that allows us to produce high-quality detection of actors like pedestrians, vehicles, and cyclists in full 3D and at very long ranges. One challenge that sensor fusion is that different sensors have different resolution and views of the world. Sensor to Tensor progressively extracts and stores information from the different sensor views of the world and brings them into a common 3D representation we call the Euclidean tensor view. So combining LiDAR, radar, image, and map information, we're able to reason about the world. So the result from just the raw data inputs is that we have complementary sensor data in 3 views: the Euclidean view, range view, and camera image. Each view contains valuable and unique information that will ultimately contribute to a holistic representation of the Aurora Driver's surroundings. To extract that valuable information from each view, these data inputs are put through what we call a neural convolution engine. Our neural convolution engine harnesses the power of deep learning to process the incoming sensor data. Here's an animation of the neural convolution engine and how it creates an enriched view of the world around the Aurora Driver. Euclidean tensor views from the LiDAR, radar, and map data get stuck into a tensor that is processed by the neural convolution engine to produce intermediate Euclidean tensor view features. Ultimately, we want to produce detection in a Euclidean view to produce rich and detailed 3D information. We do this using a Euclidean ray scatter engine that transforms points from our range view data into the Euclidean space. Each pixel in range view precisely corresponds to a point in 3D. Features corresponding to the pixel in the range view are traced back to their location in 3D and then placed in appropriate cell in the Euclidean view. This process is repeated for each pixel in the range view in an instant, generating a corresponding Euclidean tensor view from range data. Ultimately, we have migrated the information captured in range view into Euclidean view tensors that can now be fused with other Euclidean feature maps originating from other sensor modalities. At this point, feature maps from all sensor modalities are in the Euclidean tensor view. They can now be all stacked together and again processed by a neural convolution engine to produce high-quality 3D detections. The detections include properties of the object, including velocity, width, height, length category, and uncertainties on position for each detection. This creates a representation of the world around us that is rich in data derived from various sensor inputs. Our deep learning detection engine allows us to accurately construct world around our driver. Combined with our other two task-specific deep learning modules, along with an object persistence engine, we're able to seamlessly track detected actors on the road and reason about them. So that is detection. Now, if we zoom out a little bit, perception is one step in the autonomy development process. There are multiple modules in the self-driving stack that utilizes machine learning. In addition to perception, there's also motion planning, ML-aided labeling, and simulation that all utilizes machine learning and deep learning. For our machine learning development workflow, we ingest vehicle logs, combine with labels, and produce common training data that's used by multiple teams and for multiple models. We store them in the feature store, which can be visualized and explored. We then utilize the training data to train the model and the test data to evaluate model performance, various performance metrics. We go through a further series of checks to ensure the model and the entire autonomy stack performs as expected, and then deploy the model to the vehicle. And these steps are not necessarily linear either, but instead can advance in very complex iterations. Some of the challenges that we work through include the tight timeline to deploy model to vehicles, the time to market, the variety of models that we handle, variety of data types, evolving scenarios and methods. And that is why we need faster iteration cycles in machine learning development. And we need a large-scale training to quickly test out many hypotheses about improving the model behind our self-driving technology. Today, we're going to mostly focus on the training part of the process happening on AWS SageMaker. We use Kubeflow to manage our machine learning workflow. We have 3 ways of triggering training suitable for the different use cases. We can start an ad hoc training job via command line or UI. We'll have scheduled CI/CD jobs that periodically check for issues on our main line. Or we can trigger training from upstream processes, such as a new batch of data becoming available. Through either of these triggers, once our training is triggered, things happen in 3 layers: the build, orchestration, and the compute layer. In the build layer, Kubeflow consolidates container images needed for all the steps and push them to Harbor Registry and Amazon ECR before triggering the pipeline. Kubeflow supports standard authentication options such as Vault, AWS IAM roles. And in the ML orchestration layer, Kubeflow orchestration uses SageMaker training Kubeflow component built by AWS SageMaker for training. In the compute layer, AWS SageMaker training obtains the GPU instances needed for training, launches distributed training, and through S3 streaming, sends the events to S3 buckets. We can then check the logs for job progress, or launch TensorBoard and monitor the loss function for training progress, as well as other standard and custom metrics. After training, we take the checkpoint files through post-processing steps, such as TensorRT export, and then evaluate model performance with test data in the metric evaluation step. With that, we can start looking at a demo. So we start the demo by triggering a training job from the command line. The training script is triggering a predefined Kubeflow pipeline job, which includes 2 steps, a training step and a custom evaluation step. The input parameters are blurred here, but trust me, they're sent to the training script. The training script starts by building the Docker images using Bazel build for both training, evaluation steps, as well as Kubeflow itself. Kubeflow consolidates the images, pushes them to Harbor Registry and ECR, and triggers the pipeline. The step of building the Docker images will take a while, but behind the scenes, they're consolidated, uploaded. You'll see stuff scrolling by on the screen. Once this is done, SageMaker will start distributed training through the SageMaker training Kubeflow component. For the sake of time, let's speed through the process and pretend that this is only taking a second. The step of building the Docker images will take a while. Several minutes go past. Now the Docker images are built. Here we're seeing 4 of them on screen corresponding to the different components of this specific pipeline. They're then pushed to Amazon ECR. Again, this is going to take a while. We can monitor the process over that processing bar here. At the beginning of this, we start at 0%. It's now going through like 25%. It's going to take a while. We're going to speed through the process to save time. And now through video editing magic, the status is now 100%. And we can find in the logs a URL that can point us to the Kubeflow dashboard corresponding to this pipeline. Kubeflow gives us this nice UI that shows the components of the pipeline as a DAG. We can also check the configuration on the 3rd tab of this UI. Or we can click into a component, for example, the training component, and examine the input, the output, ML metadata, and check the logs for progress, and see any warning or error messages here. And in the log, we can find a URL that points to the training job in SageMaker. If we navigate to it, it shows more detailed job information on AWS SageMaker. We can also check the logs on CloudWatch. And if everything runs successfully after a few iterations, training events will start to stream to S3 buckets, and we'll be able to monitor the training progress by launching TensorBoard. So we can now launch the TensorBoard. It is only training for a few iterations, so the graphs are not super exciting. But we're still able to observe the loss functions start to decrease. The SageMaker training Kubeflow pipeline component is on GitHub and has a whole host of runtime parameters. I would encourage you to check out their documentation on GitHub. They're great. We can also check the record for all previous job runs in the same job UI and do comparisons. Now let's assume the training has completed. The next step in the pipeline would automatically start. So that's the metric step. The metric step does model evaluation through custom metrics. We can check the output from the training job just to make sure everything still looks okay. The AWS SageMaker panel, we can check that and confirm the GPU instances that we have obtained for training has now been released, and TensorBoard still looks okay. Then we can use the Kubeflow UI to find URLs of our evaluation report and examine the custom metrics performance of that model. So here in Kubeflow, we also added a step that sends a Slack notification to the user of the job. So our engineers don't need to babysit their jobs and wait for it to finish. Instead, they will get a ping on Slack when the jobs finish and are ready for human inspection. So that's how we use Kubeflow and SageMaker for a typical machine learning workflow from training to model evaluation. We've seen that it's easy to see past job history on the Kubeflow UI. A really cool feature is experiment comparison. We can see multiple jobs that belong to the same experiment and can compare them side by side. We can examine which aspects of the experiment condition have changed from run to run by comparing input parameters, and also visualize the curves on the same TensorBoard. Kubeflow allows for comparing 7 jobs on the same side-by-side view. This is really convenient for generating hypotheses, experiment on data, run the training in parallel, and quickly identify the winning solution. Overall, using Kubeflow and SageMaker distributed training allows us to quickly iterate on models. we see benefits such as faster iteration speed from ideation to model deployed in vehicle. That used to take multiple weeks. We're able to cut down to a few days to a week. And it is really convenient for debugging, as we have seen. Easy to examine the input parameters and check the logs. It's also easy for us to manage training cost. There's very little training infrastructure for us to manage. Through Kubeflow, we're also able to maintain strong lineage tracing for the safety case. From the ingested logs, to process data, to training parameters, to train model artifacts, to a full history of what has been tested on this set of model. So we have the full testing history at various levels. With that, that's the end of my talk. Thank you, and I'll hand back to Emily.
All right, thank you, Yu. So let's close things out with some resources. So first off, if you were not aware, we have hundreds of notebooks about using SageMaker on GitHub. So AWS/Amazon SageMaker examples. Everything that you looked at here today is available on these example resources, whether that's using spot instances, pointing to Inferentia, using the Kubeflow components for SageMaker to orchestrate your SageMaker jobs via Kubeflow, or using the deep learning containers, tuning your models, using reinforcement learning, using ground truth, using asynchronous inferencing, whole host of capabilities that are all available right here. So definitely this is the first place to start. Also, SageMaker is available in every single AWS account by default. So whether you're opening an AWS account at work, or if you're spinning up a free tier personal and just to do some R&D on your own side, check it out. It is included in the free tier. You can turn on a Jupyter server within Studio. You can turn on notebooks. You can run training jobs. All sorts of goodness. And with that, thank you very much. Again, my name is Emily Weber. You can ping me directly, ezweber@amazon.com. I'm also on LinkedIn. I'm on GitHub, YouTube, and Towards Data Science. So you can follow me there. And then you Guo from Aurora, Senior Manager of Perception. Thank you so much. Hope you enjoyed the session here today, and stay tuned for more. Thanks.